Okay, then it's exercise 3 at homework 8. In the last video we had exercise 2 in homework 8 and not 6 if I said that. So let's now look at exercise 3 in homework 8, and we will look at Fridays and Saturdays in the tweet count temp.txt sin data file. So let's just do that at once. So let's import some packages and let's run it, and then let us read the tweet data. So I read the tweet data, run. That should be okay. Then I can look at the tweet data, which we see that contains Thursdays, Wednesdays, Tuesdays, Mondays, Sundays, Saturdays, and Fridays. So all weekdays. But we are asked to just look at Saturdays and Fridays. So then I had to take these days out of the data frame. So I will do that first. So closing this one, and I make my own data, or my own tweet data if you want, just containing Saturdays and Fridays. So I say I want in my data Friday, Saturdays, I will have all the data from the tweet, but just when day of week is Saturday, or day of week is Friday. So therefore I run this one, and then I actually could look at my data now, and I see we just have data for Saturdays and Fridays. All the other have disappeared. And then we can go back to the notebook. And so okay, we look at Fridays and Saturdays in the tweet count temp.txt.data file. We have checked, we have done that now. And we use the model yi equal beta 0 plus beta 1 xi plus epsilon I, where these epsilons are independent and normally distributed 0, sigma in the power of 2. And where sigma in the power of 2 is equal 0.02. And we want that the yi should be the proportion of tweets with words which are defined as violenced. So yi is violence divided on total tweets. But if we go back to this my data now, we don't have anything which is violence divided on total tweets. So we have to make this column ourselves. So we have to create a new column in this data set, which is this proportion. And to do that, we can look at this line, where we say that, okay, put into my data Friday, Saturday, a column called violence proportion. And this should be the same as the violence in this data frame divided on the total tweets in this data frame. So if I now just run this line, we should have a new column in our data set, which is called violence proportion, and we see it here. Okay. And then I take this out. And then we are asked to plot average temperature against this violence proportion. So then I run that command, and we get a scatter plot. And this looks like figure 2 in the assignment. So that was 3A. Then we can go and do 3B, where we get two hypotheses. We get that H0 is there is no relation between temperature and violence. That is the same as saying beta 1 equals 0. In the model. And the alternative hypothesis is naturally then there is a relation between temperature and violence. And that is the same as saying that the slope parameter beta 1 is not equal 0. So if the slope parameter beta 1 is not equal 0, we will have increasing or decreasing violence for increasing temperatures. So if you reject H0, we know that we probably should increase or decrease the police force with changing temperature. One problem with the setup is that we may accept H0 when HA is true, type 2 error, which we do not control, which can be, and this can be a security issue. Maybe, think about it. Then it's C, and this is the same procedure and thoughts I'm now going to use as we did in exercise 2, B and C. But here everything is in C. So we are going to show what beta 1 hat must be such that we can reject H0. And of course, beta 1 hat must have a little distance to the truth beta under H0, which is beta 1, which is 0. So beta 1 hat should be either pretty high positive or pretty much negative. And therefore, the probability of rejecting H0 when H0 is true, that should be less or equal 0.1. We know that from the assignment. We can then write this as probability of rejecting H0 when beta 1 is equal to 0. That is the same as H0 is true. And this should be less or equal to 0.1. And when do we reject H0? Well, that is when beta 1 hat minus beta 1 is less than minus a number Cn or bigger than a positive number Cn. So this difference must be pretty big. I could write 0 instead of beta 1, but I let beta 1 stand because I have showed that beta 1 is equal to 0 here. So what I start to do is to find these limits Cn. And so a good rule is now to say that we reject H0 when beta 1 hat minus beta 1 is less or equal minus Cn and bigger or equal Cn. And to find the limits, I can set equal instead of less or equal 0.1. And then I do the same as we have done earlier today. I divide on the standard deviation of beta 1 hat and I then do that on all places in this double inequality, then I do no wrong. And because of the symmetry here, I can split this probability, which should be equal 0.1, in two probabilities where both are 0.05, such that this is equivalent to that beta 1 hat minus beta 1 divided on the standard error of beta 1 hat is less or equal minus Cn divided on the standard error of beta 1 hat, or that the probability that beta 1 hat minus beta 1 divided on standard error of beta 1 hat is bigger or equal Cn divided on standard error of beta 1 hat and is equal 0.05. Together we have 0.1. So then we can find the solution for what Cn must be in both these two cases. Or what minus Cn must be and what Cn must be. And we know that I haven't written it here, but we have done it before in earlier exercises. So under H0, this one is normally distributed 0.1. I don't say any more about that, so I can call it set. And this one is also normally distributed 0.1 because it's the same. And therefore, the probability that this set is less or equal a number is the same as the CDF of this number minus Cn divided on standard error beta 1 hat. And this should be equal 0.05. So now I take this one first. And then to get rid of the CDF, I have to take the inverse of the CDF. So I take the inverse on both sides. And then I just get, on left side, just get the number minus Cn divided on standard error beta 1 hat, which is equal the inverse CDF of a standard normal distributed variable of 0.05. But thinking about the symmetry in the normal distribution, we can say that this phi in minus 1 of 0.05, that this one is exactly the same as this one, minus phi in minus 1 of 0.95. You may make a drawing to see that this must be the same. And then I just times the standard error of beta 1 hat on both sides. And then I see what the limit minus Cn is. So then we can go on this right side of the line I just made and calculate when this beta 1 hat minus beta 1 divided on the standard error is bigger, such that this probability is equal 0.05. But then I just turn around the inequality sign. So instead of writing bigger, I write less. But then I have to understand that the right side of this equation is 0.95. And this is again equivalent to the CDF of Cn divided on the standard error beta 1 hat, just as on the left side here. And this is equal 0.95. And then to get rid of this CDF, I just take the inverse on both sides. So then I just get the number Cn divided on the standard error of beta 1 hat, which is equal phi in minus 1 of 0.95, and then I just times with the standard error on both sides to get that Cn must be phi in minus 1 of 0.95 times the standard error of beta 1 hat. So we now have the limits minus Cn and Cn for the rejection area. So if you remember from above, we had that beta 1 hat. So now I'm here. So we had from above that beta 1 hat minus beta 1 should be less or equal minus Cn and bigger or equal Cn. And that this probability for that should be less or equal 0.1. So now I just put in these Cn's, which make this true. And that is just putting this one into this one and this one into this one. And then I get this next line here. And I also put beta 1 equals 0 because beta 1 is equal 0 under H0. And that's actually standing here. So I put this equals 0. So then we see that beta 1 hat. So we see that beta 1 hat must be less or equal minus phi in minus 1 of 0.95 times the standard error to beta 1 hat. And beta 1 hat must be bigger or equal phi in minus 1 of 0.95 times standard error beta 1 hat if we shall reject H0. So then it's D, and in D, before I do that, I just remember formulas for beta 1 hat. That is sum of xi minus x bar times y I divided on the sum of xi minus x bar in the power of 2. And the standard error of beta 1 hat is sigma divided on the square root of the sum of xi minus x bar in the power of 2. So what are we asked in D? Well, we are asked to use the Twitter temperature data for Fridays and Saturdays and test H0 on the 0.10 significance level and conclude. Okay, I think I have done that on some wrong data, so we'll see what I get here now. Then I just so we have to compute beta 1 hat to see if this exceeds these limits we just have made. So first I then have my x values, which is the average temperature. So I run this line. That's the x values. And the y values in our exercise is the violence proportion. So I call this y, just for simplicity. Because when I call this x and y, we can just look at these formulas here when we are making beta 1 hat and standard error beta 1 hat. So therefore, so there we have our y's, and sigma 2 we know from the exercise is 0.02. That's a sigma square, sigma in the power of 2, and then I can compute beta 1 hat, which is the sum of the x minus the mean of the x times y, divided on the sum of the x minus the mean of the x in the power of 2. Let's check that that's right. Yes, that is this first one here. That's this beta 1 hat. And then I have to calculate the standard error. So then I do that. The standard error beta 1 hat. the formula was the square root of sigma in the power of 2. So we just get sigma. And we divide this on the square root of the sum of the x minus mean x in the power of 2. Let's check it. Here is the standard error of beta 1 hat. That's the sigma. So that's the square root of 0.02 divided to the square root of this sum here, which we have calculated just here. So let's see formula in notebook. We can write that here too. C formula in a notebook. Okay. Hallelujah. So here's something wrong. What's wrong here? That's a little exciting. Let's run this one. Let's run this one. And let's run this one. X. This one seems right. This one seems right. This one seems right. Divided on. This one seems right. I actually don't see the problem here. That's not so nice, actually. Maybe it's... Let's try to run it. Or maybe we have to run these packages here. Like this, so. And like this, so. And now we try this. Here's some syntax error. Where is this? Oh, I see the syntax error. There is a syntax error. So it's late for me today. Here and here. And then we can run this. And we can run this. And then we have the beta 1 hat and standard error beta 1 hat. We can actually look at them also if we want. Here, 0.04 and beta 1 hat is 0.0, almost 7. Okay. So then then we can decide if we are going to reject H0 in our example. We will reject if when will we reject? We will reject if beta 1 hat is less than this, or beta 1 hat is or beta 1 hat is bigger than this. So I have to implement that in some sense. So I say if beta 1 hat is less than what I just showed you, then reject H0. Else if beta 1 is bigger or equal this, also reject H0. Else, if nobody of this sets in, we will not reject H0, so we do not have statistical evidence against 0. So let's see what our result is. That's pretty exciting, I feel. Run. We do not have statistical evidence against H0. So this means that this beta 1 hat is not far enough from 0. So let's just check what this limit here was, just to understand that we didn't exceed it. That is minus 0.0698. And we remember our beta 1 hat. We can see this, that is positive, so that's not a problem. But let's see on this. Let's look at this, this one here. norm. This one, see how big is that? That is 0.0698, of course, in the positive sense. And we'll see that beta 1 hat don't exceed that. It's very close, but it doesn't exceed it. So we can't reject H0. But since it's so close, we have in some set some evidence, but not when the significance level is what we have set it to be. And that is actually pretty high, 0.1. Yes. So then it's the last exercise. That is E. So we are asked to, what are we asked to? Given a test, well, we are just asked to find the power function to beta 1. And then we know that the power function is actually the probability of rejecting H0 for any true beta 1. Then we just first write the power of beta 1 is equal to the probability of rejecting H0 under beta 1. And in parentheses here, we see that the test we constructed in C was that the probability of rejecting H0 should be 0.1, and it should be that when beta 1 is equal to 0, or in other words, when H0 is true. And this means that the power of beta 1 equals 0 is 0.1. But now we want to compute the probability of rejecting H0 for all values of beta 1. So then I have to find the power function. That is this. When do you reject H0? Well, we reject it when beta 1 hat minus, that's impossible to read. Reject when beta 1 hat minus beta 1 under H0, which is 0 then. I could write 0 there, but I don't do it. So we will reject H0 if this difference is less than minus Cn and bigger than Cn. But that is under H0. So to get beta 1 in play, I do just as we did in exercise 2. So I take a minus beta, so I add 0, minus beta 1 plus beta 1, that is 0. And you can always add 0 to something. You won't change anything. But doing that, I can rearrange a little here. So I get beta 1 hat. So first I add 0. And now I rearrange. So I write beta 1 hat minus beta 1 plus beta 1 minus beta 1 under H0 in the middle here. And then I divide all places on in the double inequality with standard error of beta 1 hat. And it's not a problem dividing on a standard error because it will always be positive, so we don't have to change the inequality signs. So don't think about that. And then we get this, and then I put this beta 1 minus beta 1 H0 divided on standard error beta 1 hat on the other side. So yeah, you should understand this. This is just some algebra. And then we see that beta 1, and this one, and this in the middle here, this is normally distributed 0, 1 when beta 1 is the true. Anyway, approximately, because but yes. Therefore, And then in the next line here, I just change the limits Cn, which I have been calculated earlier. So I put in the limits, and then I just cancel this out, and this out. So then we get this line here. And now we see that we have a standard normal distributed variable which should be less than this left side of the inequality, of the green inequality here. So if you look at this one, that's the same as phi of minus phi in minus 1 of 0.95 minus beta 1 divided on standard error of beta 1 hat. So this variable, which is standard normal distributed, must be less than the left side there, and it must be bigger than the right side. But if it should be bigger, then we have to take 1 minus the right side there. So then we get so then I have to, so the probability that this standard normal distributed variable in the middle is less than the left side and bigger than the right side is first the green plus this red. And if you don't understand, come to TA sessions and come to office hours and ask, because then you will understand. But very often you have to ask and talk to understand. And I think this is a little heavy, but I hope you get it. Okay, that was homework 8. Well, we are asked to actually plot this, I think. So now we have just found the power function. So this is the power of beta 1. So if you now go to power beta 1, so if you now go to the Python, we have to implement the power function. So then I need beta 1s, and since I know that under H0 we have 0, I think we have to go some to the left and some to the right, and I try with minus 0.1 to 0.1 and see if that is good enough. And then I just say that I don't think I need this n, but anyway it stands there. N is equal 46. And then I just implement the power function, which we have seen just in the notebook. So then we can run this beta, we can run this power function, and we can plot the power function as a function of beta, and we get this. And then we see that the power of rejecting H0 increase more and more as more far away we come from 0 in both directions. So that was everything. Thank you. Stop.